It's great to hear so much discussion in the lecture hall. Welcome to this year's CSIC Distinguished Lecture. Really good to see so many of you here to engage one of the leading figures in the field of tunneling and underground engineering. It is my honour to introduce Mr. Andrea Pigorini, a highly accomplished mining engineer whose career spans more than 35 years of experience in the design and construction of major infrastructure projects in Italy and indeed around the world. Andrea began his career in construction, where he gained first-hand experience in the delivery of large-scale tunnelling and underground works. He later brought this practical insight into the design sphere, joining a leading geotechnical engineering company where he managed the design and implementation of several road, railway and metro tunnelling projects. Since 2002, Andrea has been with Italferr, the engineering arm of the Italian State Railways Group. For over a decade, he led the tunnelling design department, and since 2015, he has served as the head of infrastructure engineering, overseeing some of the most complex and ambitious transport infrastructure schemes in Europe. From 2011 to 2017, Andrea also played a key role in one of the world's most significant underground projects, the Brenner Base Tunnel, where he acted as project manager responsible for supervising the works of two major construction lots. Beyond his professional practice, Andrea has been an influential leader within the tunnelling community. He served as president of the Italian Tunnelling Society from 2013 to 2022, during which time the society successfully hosted the World Tunnel Congress 2019 in Naples, one of the most celebrated editions of the event, and I don't just say that because of my colleague in the front row here. And today Andrea continues to shape the international tunnelling community as a member of the Executive Council and now President-elect of the International Tunnelling and Underground Space Association. His work reflects a deep commitment to advancing the science, engineering and practice of underground construction, combining technical excellence with a global perspective on innovation and collaboration. Please join me in welcoming our distinguished speaker for today's lecture, Mr. Andrea Pigorini.
Can you hear me? Okay. Good afternoon, everybody. My Lord, ladies and gentlemen, I'm very happy to be here with you today, this afternoon, and thanks, Brian, for this introduction and with this kind presentation. It's a real honor to me to have been invited here from CSIC and mainly by Giulia Vigiani to have this lecture today. I must say that after this introduction, I feel even more the pressure for this lecture. And also because I'm coming just a few years after another distinguished lecturer, among others, Sir or Lord Robert Mayer. So Robert, I'm very happy to be here after just a few years after you. And of course I'm a little emotional, so I hope you will forgive me for some mistake I may give, and especially in using your language. But anyway, let's start. This is my contents of today's presentation. I will give you some, let's say, definition and data of high-speed rail, and then I will take you through the evolution of tunnel design approach and construction technology, taking into account the peculiarities and challenges of our country, my country, Italy. Then we will go through the evolution of tunnel safety design with some specific operational safety design, of course, giving some clues about the aerodynamic problems we have seen for tunnels, both and for noise barriers. Then we'll go through some case study, Bologna and Florence city underpass, connecting the south of Italy, so what we are actually doing in this day, and some conclusion. I pick up this definition from UIC, Union Internationale Chemin de Fer. Basically, the high-speed rail is a whole integrated system, but the two legs of these systems are the infrastructure for new lines designed for speeds of more than 250 kilometers per hour, and the rolling stocks, especially designed specifically for train set, telecommunication, signalizing, operating condition also. But I like better this definition. High-speed rail is first and foremost about serving people, providing fast, reliable, comfortable, and sustainable travel that meets the evolving passenger expectation, that makes the train the preferred choice. I think this is something that I'm proud of as a railway engineer also, working at Italferr, the engineering company of the Italian State Railway. Some global data. We have more than 60,000 kilometers around the world of high-speed railway line. Of course, China is taking the most, more than 450,000. And there are about 13,000 of railway lines, high-speed railway lines in Europe. Of course, there are also quite a good number of new tracks in construction, about 15 kilometers, all spread around the world. And here it comes, let's say, the stretches during the time. You know, the first one is the very well famous Shinkansen in Japan. That was 1964. Then Italy came with the first stretch of the Firenze-Roma in 1981. And then the other country around the world, actually also UK, that was in 2003, the stretch towards France and the Channel Tunnel. And as you can see here, regarding Europe, 12,500 kilometers about, we can see that basically there is a kind of ramp up from years, let's say 2000 and onwards. And there are quite few countries that have European countries that have more than 1,000 kilometers of railway in operation. And of course, the high-speed railway have been built, let's say, along the Trans-European Transport Network. And regarding Italy, that means the two main corridors that cross Italy are the north-south corridors, the so-called Scandinavian Mediterranean corridor from Helsinki to La Valletta, north-south, and the green one here, east-west, the Mediterranean corridor that cross Italy, northern part across the Po Valley. And we have recognized the European high-speed network also in the ITA 50 Iconic Project book that was issued last year for the 50th anniversary of the International Tunneling Association. Because actually it's true that the railway lines across Europe contribute to reducing travel times and changing the travel habits of many people living in Europe, basically by, let's say, shortening the distance between cities. And here is the stretch in operation in Italy, basically from Turin to Milan, and then going south, Bologna, Florence, Rome, Naples, and Salerno. And basically, let's say at the end of 2009, there was a full operating network. And as I mentioned before, this gives a large reduction in train time traveling. And as you can see, that just the last line, basically between Milan and Rome, yeah, we went from 4 hours and a half to less than 3 hours. And also, again, on Milano-Roma stretch, this changed the habit of the means, let's say, that people were using to go from Rome to Milan. So we went through from 36% of using passengers using train to, let's say, basically 80%. So just 10% of people are taking plane, or the other 10% private cars. I want to give you also some clues about cost. I won't be silent about that. So basically, the total rail infrastructure investment was about, as you can see here, 29 billion euros with a design investment, civil works, track and technology. But if we also include costs for mitigation and compensatory works, this gives an overall cost of 32 billion euros. So that is the cost that was spent between, let's say, 1996 and 2018. And if you are taking in consideration the length of the high-speed railway, this gives us a unit cost for kilometer of high-speed railway line of 40 million euro. This cost is quite more, I have to say, than the unit cost for high-speed lines that have been built, for instance, in Spain and France. That is about half of this. But we got some explanation for this, because, of course, first of all, the choice to build a high-speed and high-capacity railway line. That means that also freight transport, and so that gives a maximum design gradient of 1.8%. And that means requires construction of many kilometers of tunnels and bridges, beside the orography, of course, of Italy. That is quite challenging. And we have, of course, in Italy, a high level of seismicity, a geological and geomorphological complexity. As I mentioned, additional mitigation and compensatory works delivered for the surrounding areas. And last but not least, I have to mention also the type of contract, with a selection of the Italian general contractor with a non-open tender. So that's give, let's say, the explanation of the difference of costs among other countries. And this is just a slide to recap, basically. So around 1,000 kilometers of high-speed railway network in operation, 350 million of passengers on our train in these 10 years, and 32 billion euros of investment, as I mentioned before. And these are the stretches both in operation and under construction. The dot line are under construction, so Milano-Genoa, Milano-Verona, let's say, and Naples-Bari. And the length of each stretch with the kilometer of tunnels and bridges for each stretch, but probably it's more clear, these slides here, that it's give the kilometer of tunnels and bridges and viaducts and cutting and embankments, and on the right side, the percentage of this. So basically, as you can see, the last stretches, Bologna, Florence, Milano-Genoa, and Naples-Bari, has very long stretches underground, with 90% of the stretch of Bologna-Florence, but also Milano-Genoa and Naples-Bari are more than 50%. And that are the total figures. So in operation and under construction, we are talking about 1,500 high-speed kilometers of high-speed railway, with 330 kilometers, or more than 20% of tunnels, and also a good number of kilometers of viaduct. Now I want to take you through, let's say, the evolution of tunnel design approach and construction technology, associated also to this country here, that is a very peculiar country as for the orography, Alps mountain range and northern border, connecting Italy to the rest of Europe, 750 kilometers. Apennines mountain range that cross Italy north-south, 1,500 kilometers. Very urbanized country, and less than one-third on flat area. Also, from a geological point of view, well, we have difficult geological and geomorphological conditions, major fault zone, Apennine mainly formed by structural complex rock flysch with squeezing and swelling hazard, rock mass often bearing methane gas with explosion hazard. In main city, on the other hand, the subsoil is mainly consists of alluvial deposit with the water table close to the surface, high seismic risk in many Italian regions, and landslide hazard on more than 20% of the national territory. And to overcome this obstacle, since, let's say, Vespasiano, building tunnel was the correct choice, let's say, to reach Rome and to connect cities and countries with railway line. And starting from, in this journey, I would like to start from this 1871, that is the Frejus tunnel. Actually, the Frejus tunnel is the actual railway tunnel that is still connecting Italy and France by train, is only one. We are waiting for the Monceniso tunnel, but I guess we will have to wait another 10 years probably. And that was a tunnel, a single bore double track tunnel, 12 kilometers long, where for the first time was utilized the compressed air drilling machine with a compressed air, so we use compressed air. That was a kind of ancestor of the modern jumbo. And jumping to 1934, the great Apennine tunnel between Bologna and Florence. This was a conventional excavation tunnel with a sequential approach, a sequential excavation method, the so-called, with small tunnel section. As you probably can see here, or probably I can try to do like this. That's right, yes. Okay, here in this longitudinal section, you see that basically the main principle of this was don't remove an amount of ground bigger than what you can directly replace with structural support of tunnel. So basically, what we have is let's say the bottom tunnel, the tunnel below, that was excavated first. Then it came the crown tunnel, this little one here, some shaft to ease the muck out of the material from the bottom tunnel, and then the enlarging process of the tunnel was put in place, also of course using temporary support made of wood at that time, and then the final lining let's say at the back of the tunnel face, mainly done with masonry, and thus so is the main, let's say, principle for this method. Then it came the Roma-Florence one stretch, the first one, built in 1977, between 1977 and 1992. Basically, the stretch is 240 kilometers. 1/3 of this is underground, and at that time we mainly used the new Austrian tunneling method, NATM. And the main principle behind this method was that the rock mass has to be considered as the main component of tunnel support. So the primary support is assigned to enable the rock to support itself. And the method introduced the use also of a new technology for that time, that was the shot rig that was fully in place. And as for the Ramsey-Parker rock mass classification, half section was and partial excavation was to be used in bad rock condition, as you can see also here in these pictures. Coming to the Bologna-Florence high-speed line, so the new line between Bologna and Florence, 1996-2009, we had recognized also this masterpiece, let's say, in the ITA 50 conic book project, and basically is a kind of base tunnel. It's not one tunnel actually, there are 9 tunnels with a length of 73 kilometers of tunnels. It's a double track, there are 9 double track tunnels below up to 60 meters of burden in extreme severe rock. And that tunnel has been excavated with conventional full face excavation and rock mass deformation control by means of ground reinforcement performed ahead of the tunnel face were applied to deal with adverse geotechnical condition. And as you can see from the picture here, we got the picture of the tunnel face of the Canonic complex, where you can see scaly clay with poor geomechanical parameters with boulders included in that phase. And the new Bologna-Florence stretch was designed and built according to the Adecores method, analysis of controlled deformation in rock and soils, and the main principle behind this approach, this methodology is, of course, beside the clear separation between design and construction that it's a must, the full section excavation also in bad ground condition. The tunnel studies the 3D problems with the necessity to understand the behavior of the tunnel core face, and the tunnel core face use an instrument to control deformation and the stability of the tunnel. So you have to prevent deformation occurring ahead of the tunnel face to prevent the deformation acting also on the preliminary lining that will be installed later on. And these are some pictures of the construction phases. Usually we have a pre-confinement, let's say ground improvement ahead of the face and around the cavity to improve the tunnel core face behavior to control the deformation. Full face excavation usually done by hydraulic hammer. Invert, shot rig ribs, and sometimes also invert preliminary lining with ribs and shot rig to prevent tunnel face and invert arch deformation, especially in bad behaviors, let's say. Sometimes you have to cast the final lining at the invert close to the tunnel face to close your section, structural section at the tunnel face. Then, as usual, waterproof membrane and crown and side walls concrete final lining installed at a certain distance of the face. So basically, let's say at 150 meters from your tunnel face, you could get the final, let's say, structural component of the tunnel all in place. So your tunnel is finished, is completed, and the structural point of view is everything has been done, let's say. And with this method, the Bologna Firenze was excavated with a good production that gives from, let's say, from 1.5 up to 5 meters per day. And actually, of course, that tunnel that also were quite long, also 19 kilometers, were not excavated only from the adits, but they have 15 lateral adits also, and that gives an average advance rate of, let's say, from 1,000 meters to 2,000 meters per month, excavating more than 30 tunnel face at the same time. And to complete this, let's say, time lapse, I want to talk a little about Naples Bari, that is a stretch under construction now. Well, it's very challenging. We are crossing again the Apennines, and the tunnels of the existing historical line are quite famous in Italy. Like, for instance, Cristina Tunnel built in, in 1870 with great high deformation of the lining, but also this one that has been built in 1990, so 35 years ago, experimented very high deformation, as you can see here from this arrow. But nowadays, for instance, this tunnel has been built been completed just a few days ago, and yeah, is another things, let's say. And this stretch is, we are in marine deposit, pelitic and calcareous rock, turbiditic formation, that is an alternation of sandstones and calcareous rock with clay and clay shales. And we have also very important thrust fault. And so basically this material has an heterogeneous composition because there is an alternation of rock with different characteristics, as I mentioned, and structural features because of the tectonic history of the region, so thrust surfaces, faults, and joints. And you can see also from this picture from the bore log, significant contrast in mechanical properties in the flysch of Faeto, and heterogeneity and structural features in the scaly clays of features of Flysch Rosso. And these scaly clays basically are formed by this platy-like shape called scales, and the fissures are frequently smooth and often also slick inside as a consequence of the shearing condition. And you can see this also from some laboratory tests, triaxial shear strength test. And what I would highlight is that especially for residual condition here, the cohesion go to 0 and the friction angle is very, very low. So here also you have to prevent deformation occur. You have to try to prevent to go to the residual value of the strength parameters. And at the surface, as was mentioned also before, actually it's difficult to prevent this, and so the extensive personal geomorphological features can be seen in the area with unstable areas such as undulated surface with depletion and accumulation zone, as you can see here also in these pictures here. So this is the context, and in this context we have thought that going underground, deeply underground, let's say, has been considered the most effective solution to mitigate the landslide risk underpassing the critical areas of unstable slopes. So the new line, 120 kilometers, was built mainly underground, more than 50% of the stretch. Among this 50% of the stretch, that was about 55 kilometers, 48 kilometers were excavated by TBM APB, and 6 of them, as you can see here. There are quite 4. We need 4 are in operation, and the other are coming. And why? Which is the advantage of using APB TBMs? Of course, you can reduce ground deformation because you can control the deformation at the face by means of the air pressure balance machine. With the shield and with the precast segments, you can guarantee to control the deformation and the tunnel stability very close to the tunnel face, because the shield is there and the concrete lighting will be put in place 10 meters behind the tunnel face. You can also minimize ground rock disturbance and the tunnel boundary, of course. On the other hand, let's say you have to take in account in squeezing ground condition and study the shield length, that probably must be a short one, and to minimize potential blocker in squeezing ground, you have to taper it to accommodate a bit of deformation in this case. High thrust force also has to be installed in case of blockage. From a for a construction process, of course, the quality of precast segmental lining, it's well known and it's better than a cast in situ concrete. The automatic control of TBM operation is something that it's done, and so you can control your parameter in real time and check that everything is going as is foreseen, let's say, or as for the design requirement. Of course, the speed, the construction time reduction also is a plus. From a safety point of view, works operate in a safeguard area due to the presence of the shield. And also in a explosion hazard in gas-prone environments, it's a plus, because you can control the gas coming with the APB machine, because you got the air pressure at the face of the tunnel that can prevent the methane gas to rush in the tunnel. Now I want to go a little bit about tunnel safety design, operation safety design, and some aerodynamic problems that we have studied. Okay, the safety regulation, of course, changing during the year. So since '97, there have been quite a change, but I want to mention the technical specification for interoperability, TSI, that is the European standard, and namely the safety in railway tunnels, that is a specific code that deals with safety in railway tunnels. And this has been adopted also from the Italian code recently. And due to this, also to these codes, but also of the fact that of the increasing of the train gauge, of the increasing of the speed of the train, we went from a radius of double track tunnel from 4.4 meter up to 6 meter, because, for instance, we had to increase the sidewalk from 0.5 meter to half a meter, from more 1.2 meters, and other issue with the safety equipments, for instance. And this gave us, let's say, an increasing of a clearance area from 47 square meter up to 87 square meter. And if you see this section, let's say, with the time, basically we went from this here in 1950, 1960, that was 42 square meters, up to this one that has a clearance area of the last one that are using 87 square meters. And below you can see also not only the internal section, but let's say the excavation section. And if you go down here, what we can see is that to have, let's say, 87 clearance area in the tunnel, you have to probably excavate something like 150, 156 square meters. So that gives you a ratio between the two areas of 1.8. That's a lot of MAC to manage, of course, but it is due to also to this effect here. The already have high-speed trains in tunnels. The passage of high-speed trains through tunnels generate atmospheric pressure disturbance that propagate along tunnels at the speed of sound and remain inside it because it's reflected from the other adit, and it comes back, and this oscillation until they dissipate due to the friction of the surface of the lining. And the rapid pressure variation may cause damage, let's say discomfort at least, to the passengers. And the TSI infra say that you have to control this overpressure, and you don't have to have to exceed the 10 kilopascal kPa during the time required for the train to travel through the tunnel. And I would try to go with you along these graphs. So here it's you got the timeline. Here is the tunnel length from one adit to the other adit, and here you got the pressure and again the time. So basically at T0 the train is entering the tunnel with his nose here, and of course it goes with the speed of the train, but at the same moment a pressure wave positive induced by the train nose is measured as a section. Take this line as the reference line where the instrumental measure is, let's say. So at T1 is the time that the wave of pressure reach the mid of the tunnel and give this overpressure. Then it comes the entry into the tunnel. The tail also is entering. So this is the nose, and this is the tail of the train that is also going with this, let's say, speed. And at T3, the wave, this wave generated by the train tail, it reached here. Sorry, this one. It reached the measure, and this is negative, so this gives you a drop down of the pressure. And then what happens here, it comes the wave of the nose that is reflected from the other adit and comes back towards the station, that is T4, it is again negative. And then at T5, finally, here, we have the train that is passing just the measuring section, and this gives a depression. And then also the tail of the train is reaching the section, and in this case it gives a positive variation. So this is the theoretical, let's say, curves that you can have. This is for one train. Actually, for a double track tunnel you may have, and of course you have to study also this, but it's more complicated, so I won't show you, but the crossing of the two trains. So of course you should add this to also to the overpressure generated by the train going in the other direction. But what we did is a trial site in Roma Napoli stretch that was in 2009. So what we did is put some instruments in 3 sections. Pressure, temperature, and height density and velocity we measured. And what we have found out is that, well, we did with the software before, and we used a software called DB Tunnel from Deutsche Bahn. That was a monodimensional software, but as you can see here, the 3 points of measure here, measuring the pressure, following the graphs I showed you before, basically the 3 points give exactly the same result. So it's the pressure, the changing the movement of the wave of the pressure is a 1D phenomenon. So it can be well represented by the software 1D. And also the software was very reliable because actually this here in black, but probably is a little bit hidden by the other colors, you got the software data. So basically what this shows us this is that the software was working well, and that we could use this for also understanding what was going to happen with the train crossing critical condition. By the way, when measuring the higher velocity, this is not exactly the same thing because there is turbulence. So of course, in this case, you cannot say that is a 1D phenomena, but you should study as a 3D phenomena. But coming back to, let's say, the wave pressure generated by the train in the tunnels, what we have discovered with this analysis is that basically you may have with this kind of tunnel that had an internal surface of 82 square meters, you may have some problems because you are very close to the 10 kPi line, and basically we have seen that with a critical length of between 1 kilometer and 0.3 and 1 kilometer 0.8, you can reach nearly 9.5 kPa. On the other hand, for longer tunnel like this, that is called Albani, that is more than 80 kilometers, 8 kilometers tunnel, because of the reflection of the wave, you don't have this kind of phenomenon. So the overpressure is less. So you don't have to worry about that. But this is one of the causes of why we increase the area of the double track tunnel for the new high-speed line. And I want to show also this to you. This is the same effect, but not in the tunnel, in open air, let's say. So here is the barrier, and now you can see the train that is passing, and you can see the nose, and then the tail that is passing. So what we did in this case, again, a field test, in order to evaluate the action to be considered in the structural analysis, to design and to check the life of this noise barrier. We installed aerodynamic pressure along the panel of the barrier. We installed, and they've been installed on the other side of the barrier, but then they are connected with a PVC pipe in the internal side of the barrier. Accelerometers on the post of the barrier, and also strain gauge, let's say, at the bottom of the post. And what we have discovered here. Okay, of course you can have the time history of the pressure. Basically what happened is that you get the train nose that goes up and immediately down. So it is an overpressure, and immediately afterwards is a negative pressure. Then this here little are the cars of the trains, and namely the space between the cars of these trains that gives this little variation of pressure. And then of course it comes also the tails of the train. And this is a general, let's say, point above, but if you see these graphs here, you could have a different pressure, of course, according to the height of the barrier and according to the type of the train. So, for instance, the ATR 1000, that is a little bit bigger than the other trains, gives you in this part a pressure that is a little bit higher than this train here. But on the other hand, because of its aerodynamic that is better than the other one, the pressure here is a little bit smaller. We have also measured the acceleration, of course. So acceleration induced by the time pressure that I've shown you, this one. And this generates loading and unloading cycles and therefore fatigue stresses. So what we did then is to use an SFD analysis, computational fluid dynamic analysis, to model what we have found in the trial test. And so here you can see the pressure. The red one is the wave pressure, let's say, and immediately after a negative pressure. This is on the nose, and on the back is exactly the same. And so what we were able to match, let's say, and to fit the relative pressure versus time experimental data towards the CFD analysis. And then, having done this, we could use this data in a FEM model, a structural model, matching, let's say, the accelerometers that we have measured in the field test with the FM model, and the fit was quite good. And this is for the strain gauge, and the accelerometer is below, actually. So this is the data of the strain gauge coupled, let's say, between the theoretical value and the measured value. So with this, basically, we didn't have to, let's say, to do any more tests, because now we are able, let's say, through a trial, after having used the trial test result, checked with CFD analysis, then the FM analysis And so we can calculate the fatigue damage calculation of the barrier, and also understand the residual life of the structure during the time. So this is used for, let's say, the design of new barriers. Now, coming back to tunnels, I want to talk a little bit about the Bologna-Florence cities underpass. And I have to mention that some of this experience that I'm going to talk about have been done also with GCG and with Robert Mayer. So it's a pleasure to me to say something also to you about this experience. The Bologna underpass is 10 kilometers of underground stretch. So again, the choice was to underpass the city of Bologna with tunnels, 10 kilometers long. And that is these dot lines here. And basically, the choice was to have a TBM, twin single-track tunnels, just below the existing railway embankment here, to avoid, let's say, to go underneath buildings. And of course, we had to have also some conventional excavation, because before entering the underground, the new underground high-speed station, that is this rectangular box here, we have to put the two tracks, let's say, close together at 4 meters, 4.5 meters, and so you need to have, let's say, a double track conventional tunnel and not a single track TBM tunnel. From a geological point of view, in Bologna we have mainly alluvial soils, that is heterogeneous ground condition, high variability of geotechnical properties as usual for this material. The water table was quite close to the surface at the south and north section, likely in the middle that was below the invert of the tunnel. And the design choice, as I mentioned, for Bologna, but it's the same thing for Florence, is to have two single-track tunnels, use an APB machine, because that was the ground good for this kind of machine, protective measure for existing structure where needed, I will go through in a while, and of course a deep monitoring program to control predicted design values and TBM operating parameters. This is the tunnel section, internal diameter of the tunnel 8.3 meters, thickness of precast concrete lining 40 centimeters, annual gap between the exodus of the lining and the excavation surface 15 centimeters, and connecting tunnel every 500 meters. And this is a PB machine. It's not, I'm kidding, don't worry. But I wanted to show you, because this is Mr. Lovat, Richard Lovat. Is more than 92 years old. He's still in good shape. And on the right we got the APB machine, the Lovat APB machine, the two Lovat APB machine that excavated in Bologna, 9.4 cut diameter and the length of 10 meters. And this is the launching shaft of the two TBMs. And coming to the protective measure, of course, we know that the transversal settlement induced by tunnel excavation are well represented by the normal probability distribution Gaussian curve, as for field measure. And the curve is characterized by maximum settlement value and WV max, and by the I value, the inflection point, that is related to K, that is a factor correlated with the type of ground, and with Z, that is the depth of the tunnel, the distance of the tunnel center line to the surface. And we know that W max is correlated to the VP, where VP or VL, volume loss, that is the area of the trough, of the Gaussian trough, correlated with the area of the tunnel excavation. Okay, and of course W max is also a function of the diameter of the tunnel, of K, and again of the depth of the tunnel. And so we have this transversal curve here, and we know that we have also an S curve, a longitudinal curve, so that the settlement curves also ahead the tunnel face. And actually, when excavating with an APB machine, you usually have settlement ahead the face, a settlement along the shield, a settlement after the shield tail is passed, and eventually settlement due to the long-term deformation. And with this volume loss, the prediction of ground settlement has been done. Usually what is used to do is to vary the volume loss, and for Bologna was 0.41% up to 1.5%, and also the key parameters vary because it should, depends on the type of ground, and for Bologna was 0.35 and 0.5. And then you can check with this Gaussian curve, you can check your buildings damage. Of course, you can have this kind of assessment and eventually have a preliminary assessment done with only referring to the maximal settlement value, or otherwise you can have an assessment done with the green field condition, eventually taking into account also the relative stiffness approach, so the difference between the stiffness of the building and of the ground, and eventually also a soil structure interaction analysis. If you reach a damage category according to Mayer, Barlan, and Taylor evaluation of damage more than 2, and this is what is done. So basically, if it's more than 2, so from 3 ahead, you have to design mitigation measures. And for Bologna, we didn't need it for buildings, but we need for underpassing 3 brick arch structure rail bridge. And I want to talk briefly about this building here, that is the Via Emilia Railway Viaduct. That is a brick arch structure, length 112 meters, width 11 meters, total 8 arches, and the principal arch above the Via Emilia Road was 60 meters span, and the secondary arch was 8 meters span. And above there was the operation of the Florence railway, Bologna-Florence railway line. At that time, the only railway line that was connecting North and South Italy, so you can imagine. And the distance between the tunnel crown and the foundation of the viaduct was just 10 meters. Luckily, as I mentioned before, the groundwater was below tunnel invert, and the ground was, let's say, mainly was alluvial but mainly gravel and sandy gravel above the tunnel crown, with some silty and clay also lands up here. So we had some constraints that were we need to guarantee the continuity of the railway lines, so it was impossible to work on the bridge. We have to guarantee the continuity of road operations, so it was impossible to have crowd treatment below the foundation of the bridge. And also we couldn't use private area around the viaduct, so it was impossible to build shaft to eventually go for compensation grouting. But what we did again compensation grouting, but from trenches. And actually it was, I guess, the first time, I will skip this, but I will come back in, the first time that let's say, banana shape drilling operation was performed. But coming back to this, sorry. No, here, okay, sorry. So, what we did, we did acceptable limits of distortion for the viaduct were defined through a complex structural analysis of the brick structure. This analysis demonstrated that the viaduct could be brought to structural distress both by differential settlement across an individual arch or by relatively small rotation also of any individual pier. Thus, an interactive domain like the one that is shown here, it was defined in the formation space, delineating safe combination of pier rotation and arch differential settlement. Control of rotation of the piers by compensation grouting was considered to be potentially difficult, since most of the piers have a very narrow footprint. So consequently, a much stricter emphasis was placed on control of the differential settlements, and this ensured that the maximum possible range for a settler pier rotation was available for compensation grouting control. So basically, we concentrated, as I mentioned, on this, let's say, differential settlement, one on 4,000 and the red one, mandatory grouting, one on 3,000. That means very little differential settlement for, let's say, the span of 8 meters and the span of 60 meters. So very, very little differential settlement. As we know, let's say, compensation grouting, we quite know how it works. So it consists of timely injection of grout between the tunnel and structure to be protected. Of course, we know that tunnel-induced settlement, as I mentioned before, and we have to, let's say, compensate the settlement not at the surface, but let's say in the space between the crown and the foundation. With installing pipes, pre-installed grout pipes called tuba machete. Injected grout induced heave, which reverses the tunnel-induced subsidence, so that structure to be protected only experience small and acceptable level of settlement and or distortion. And this is the site, as I mentioned before. So to, of course, to dig this kind of boreholes, you have to use this symmetric utensil. And we 96 directional drilling, which casing of 114 meter diameter with grouting posts every 15 centimeter were installed. The maximum drilling length was 68 meters, and the radius of this banana-shaped rigs, tuba machete, eventually was 90 meter. And these are what we successfully exceed. So basically, you can see here, we have measured the settlement with water level gauge at different side of the bridge. And basically, what we had at the final, very little settlements, and especially very little differential settlement. As you can see here, is also plotted, let's say, the volume loss 0.2% longitudinal curve. And so, as you can see here, also with a very little volume loss, the grade of the longitudinal curve would be higher than the trigger level of 1/3000. I didn't mention, but I will do right now, this fact. So basically, we had to inject, to prepare this kind, the ground that I showed you before, 712 cubic meter of preparatory works, because actually you had to close this kind of soil so that it's ready to react to the secondary injection that is performed while the TBM is passing. So this has been done in advance. That was basically 7% of the total injected volume. And during the TBM crossing, we injected 145 cubic meter. That gives a GEF, a ground efficiency factor, that is the heave volume divided by the injected grout volume of 10%. So that means that you need 10 liter per square meter of surface to obtain a heave of 1 millimeter. And so that's our good, let's say, behavior and results. And so the two tunnels were completed. That was in 2006, with a good average production of 10 meters per day, and with a maximum production of 36 meters per day. I would like to talk to you now about the conventional tunnel. As I mentioned before, in Bologna, we had also some stretch excavated with conventional method. And this is the stretch, just, let's say, this is the place where the high-speed railway station has been built. So this is the stretch between the TBM tunnel and this was about 100 meters long, a little bit more. So between the twin tunnel section and the underground high-speed railway station, a 12 diameter double track tunnel was constructed beneath these two buildings here that you can see. So an extensive, using conventional method, an extensive protective measure were put in place, which consists of both vertical and horizontal J grouting Of course, vertical geogrammy was possible also not where the building were, but so we had to excavate the tunnel just below these two buildings by stage with horizontal ground improvement. The tunnel axis is located at minimum depth of cover of about 17 meters. This is the maximum depth, but usually 17. And the subsoil is constituted by fluvial deposit, mainly by silty clays and clay silts here, T1 here. But also lines of sandy silt and silty sand were in place. Both formations, anyway, they're very characterized by very low permeability of -8 meters per second. And the water table was 5 meters below ground level. The two buildings overlay the excavation, this one and these two, are quite different. They have been constructed with load-bearing masonry walls on strip footing with reinforced concrete floor slabs. And the 107 is a 5-story structure, the other one is a 2-story structure. And what we have seen is that in this case the settlements were very, very high. As you can see here, this is the transversal curve. This is millimeters, so we reach 20 centimeters. That is a very large settlement. And this settlement occurs, let's say, also ahead the tunnel phase. These are the distance from the section STE that was this one here, this one in the middle of the two buildings. And so basically the graphs show that the settlement were quite important also before the tunnel phase was reaching the settlement measurement station. And so the most of the settlement occurs ahead of the tunnel phase. And the volume loss at the end could estimate of 5.1%. That is a huge volume loss. And this volume loss actually was, let's say, measured and observed mainly during grouting operation. You can see here in these graphs, these show you let's say the settlement along the time while excavating the stage 12 and 13, these two here of the conventional tunneling. So what you can see here that the settlement during GR, that is while we were doing grouting, was quite high, while during the excavation of the stage, the settlement was not that big. And again, the same thing for stage 13. And what we discovered that the geogrammy caused a large increase in pore pressure as we measured by this piezometer close to the tunnel, well, a 40-meter distance from the tunnel, otherwise the geogrammy would have damaged it. And as you can see here, we experimented a quite increase in overpressure of about 30-35 kPa. So this probably induced this kind of settlement. So this is something that you have to cope with if you are designing a grouting grout treatment on the tunnels in this kind, of course, of soil, not in sandy or gravel material. But in this kind, you have to take in account that this could be possible because, of course, the protective measure was needed to prevent stability problem, but actually gave a large amount of settlements induced by this increase in water pressure induced by the grouting that, as we know, it goes up to 500 bars of pressure, and so if it could increase the water pressure also. And from building side, what we've seen is that actually the building 107, that is, let's say, the highest one, the rigid one, respond rigidly and simply tilted. So the majority of damage of the building could be attributed to horizontal distortion, but actually were quite very slight to slight. On the other hand, the building 106, a large settlement distortion resulted in jamming of doors and windows, and the crackings, of course, particularly in the hogging section of the trough curve, with a moderate level of the damage. both centrifugal modeling and field data indicate that the distribution of building weight due to tunneling can significantly influence both the response of building itself and of the soil. And the rigid buildings tend to redistribute their weight and embed into the soil, as we have seen also here in Bologna, while the flexible buildings simply deform according to the greenfield settlement profile. I want shortly talk about Florence, that is very, very, let's say, similar to Bologna, because again we have about 5 kilometer length tunnel below the city with a high-speed station actually designed by Sir Foster. So Norman Foster designed these cities, this station, sorry, and actually is now under construction. So again, 2 APB machines, they just started here and they are, let's say, 1/3 of the stretch, the 2 TBM. These are some data of the TBM, but basically is a very typical data of an APB machine, and the diameter, the geometry of the tunnel line is just the same of the Bologna. And this is the thickness and the geometrical requirement. And from a geological point of view, again, we are alluvial soil, as I mentioned. Basically, in the first stretch was more silty clays, and then now here in this stretch is more sandy gravel soil. And we are working with this operating construction controls. I want to show some data about this. Basically, we are doing a summary of design forecasts every 500 meters. Putting all the geological and geotechnical information beside the main interference information, and giving to the contractor all the, let's say, main TBM parameter and the related alert and alarm threshold. So like phase pressure, density of the material in the excavation chamber, weight of the excavated material, pressure and volumes of the 2 competent ground of the backfilling and thrust force. And I want to show some of this data. This is the, let's say, the check of the weight of the excavated material. So 2 balance, weight number 1 and weight number 2 are installed. The balance are on the conveyor belt just after the screw conveyor. And this gives a theoretical value has been estimated for each, let's say, for each single rig, that is around 210 tons. Some, say, attention and alarm value, percentage of the referring value are designed here. And here you can see if you are staying in this, in this threshold value. Sometimes it is not, so the green, for instance, weight went above. But what we are doing is so a correlation of the two measure here, so a mutual deviation of the 2 balance. And so basically, in this case, what you've seen is that one of the balance went more than the trigger level, but actually we checked that was a malfunction of the balance. And again, this happened here. Eventually here you have both balance that go above the alarm trigger value, and so that was a real over excavation, but actually we didn't experiment any kind of settlements, but we had to inject more backfilling routing at that challenge. Backfilling routing. The backfilling routing, in an APB machine, it's very important to do, let's say, together with excavation. So while you're excavating, you have to backfilling your precast lining. And this has been done by, so immediately in the shield, basically, the tube are installed in the tail shield, from 6 points, different points, and this has a theoretical value of 7.2 cubic meter per advancement. I have to check that this volume is really installed, and sometimes we went above, but this was a problem of injection line washing, so nothing to do with a real problem. But actually sometimes we had also experimented this damage of the tail seal brush. You know that in the tail sheet there are the internal brushes, and as you can see probably in this movie here, this was a big component that was coming out between the shield and the concrete lining because of the brushes that weren't working properly, so they have to be changed, and then the works could proceed. And this is the control of the phase pressure. We had 10 pressure sensor in the APB chamber at different level, and the pressure of the crown elevation was to be 0.8 to 2.7 according, of course, to the change and in function of the depth of the tunnel, the groundwater, and so on. I will show you in a while. So this was the reference value, and with a tension and alarm value, and this showed that the pressure at the crown, that is the most important one because it's the higher one, so you have to have the pressure also at that point, otherwise you are not excavating in an APB mode. And the pressure by design was calculated by Cobb, so basically it was the active earth pressure with plus the groundwater pressure plus the surface load plus 20 kPa. It's also how it was calculated, the reference pressure on the ground. And you have to check also the tunnel weight of the material in the excavation chamber. So you have to be sure that the density in the chamber is equal, let's say, in all the height of the APB machine. So you have to check that the density that was estimated of 14.5, basically calculated by the different pressure between the sensor, the higher sensor and the sensor in the invert. This value should also be the same value if you calculate this doing the difference of pressure between the other sensor of pressure in the phase chamber. And actually, as you can see from the graph, this is mostly like this, but we had also some cases where basically the density was not at that level, so it was kind of 1 or 10 kilonewton per cubic meter. So in that case, of course, it is not real APB. That is liquid and air, so that is not working properly. And you could have some problems if this is something that is happening often. Last thing that I want to show is also the thrust forces. You have to take in mind that usually this APB, but it's quite common to have 38 thrust jacks. This is let's say a 10-meter machine. 19 shoes, so two thrust jack every shoes, and 5 of these were instrumented. No, so we think that all the thrust jack push with the same level of pressure, but it's not at all this actually, as you can see here. So basically, the group A on the crown contribute to the total, let's say, to the total force about 10%. The section group E and B, the lateral one, let's say above the center level, 35, and the most part of the pressure, 35, is in the lower thrust jacks, because you have to, let's say, keep the APB machine with the, let's say, with the face with the cut red going up, because for the weight of the machine it tends to go down, so you have to push a little bit more with the thrust cylinder in the invert, and this has to be taken account when calculating your rebars for the precast lining, especially the circumferential bars, taking this pressure of the thrust jack. But anyway, this went quite well, so the measure was according to the trigger level. And just to very quickly give you some data about the topographic section, is a typical section, so I won't go, but basically we get point on the tunnel axis, leveling point on the tunnel axis, and transversal section in the road when it was possible. The settlement, what we have measured, were very, very little in this case, like 5 millimeters. These are all longitudinal tunnels axle settlements. As you can see, less than, let's say, 15 millimeters for the TBM1 and even less for the TBM2. And this was the typical, let's say, value, a longitudinal section with few millimeters ahead the tunnel face and arrive then to 1 centimeters. Sometimes we have experimented also a positive pre-subsidence, probably due to some foam that was going towards the surface, and so we had also this, but was very, very, very occasional. And this is the graphs with the chainage and the settlement for the 2 TBM. So you can see that basically the value that I mentioned before, and we don't have a real, it's a difference between TBM1 and TBM2, and also as volume loss is the same thing. So basically, sometimes is higher the TBM1, sometimes is higher the TBM2. And anyway, I'll show you a transversal section with the settlement of the TBM1 that is a little bit less than the TBM2, but is again less than 1.5 centimeter. And the K value and the volume loss are quite in accordance with what we thought it would be. So complied with TBM design parameter was good, limited excavation induced effects, and confirmation of design prediction. And this is an Eric machine, so now also Eric is happy about this. I won't talk about the Chinese machine because we are using in these days, and I don't know yet how I should talk about this. Connecting the south of Italy, just to tell you that we are working after this 1,500 kilometers. We are now working the south with 600 kilometers between Salerno and Reggio Calabria and all the Sicilian stretch, Messina, Catania, Palermo. We are also working connecting Italy to the north with the Brenner base tunnel. So we're working on the, let's say, Italian, we call south access to this base tunnel, both Moncenisio tunnel with France and Brenner base tunnel with Austria. And again, a lot of kilometers of tunnels are on this stretch, more than 73% for Salerno, Reggio Calabria, and 50% in Sicily. And we have to recall that between Calabria and Sicily there is a bridge. With that we hope that is going to be built. Actually the contract has been re-signed with the contractor, and this would be a simple single span suspension bridge, 3,300 meters, more than, well, the longest one is actually a little bit less of 2,000 meters in Turkey, featuring with 2 towers, 400 meters tall. So you can imagine, and also a lot of tunneling, by the way, especially Sicily side, to connect the bridge to the city of Messina. And this is my basically last picture before the conclusion. These are the number of TBMs that the green are working. Actually, it's not updated because we're not at 4, but we have 6 TBMs that are working today, and will become 25. And I have to mention that till now, in all the life of Sicily, only 3 TBMs have excavated. So this is an enormous, let's say, investment for building a good railway line also in Sicily. Some conclusion. The widely planned construction of high-speed railway line across Europe contributed to reducing travel times and changing the travel habits of many people living in Europe. Over the past decades, advancements in tunnel design approach and construction technology have significantly enhanced the tunneling industry. This paved the way to an extensive use of long underground stretches for high-speed rail infrastructure. In Italy, the conventional excavation method has been widely used to build the high-speed railway network already in operation. This method allows for the complete industrialization of the tunnel construction through full-face excavation while controlling the deformation of the tunnel face advanced core with ground improvement applied where necessary. On the other hand, TBM APB excavation has been used to tunnel beneath the city of Bologna and Florence, that is still ongoing. In both conventional TBM excavation, a large monitoring program has been adopted controlling design values and TBM parameters. A large infrastructure investment program supported by the European funds is currently underway to expand the high-speed network to the southern region of the country. And due to the geographic context and to minimize soil consumption, I'm also the ITI president, so this is exactly true. Tunnel for a better world, that is our slogan. For this new rail infrastructure has incorporated long underground stretches, therefore enhancing an extensive use of special design TBMs, that is usually dual mode and APB TBMs, to operate also in challenging geotechnical context. Thanks for your attention, and I just would like to thank my team, because I prepared this presentation with my team, with Alessandra Sciotti that is here, the head of the tunneling department, and her team in Italferr. So, and thank you for your attention this evening.
So, my lord, ladies and gentlemen, it is my great pleasure and honor to offer the vote of thanks after this truly comprehensive and inspiring lecture by Andrea Pigorini, President of ITA and Head of Infrastructure Design at Italferr. So this afternoon we've taken a very long journey, a very comprehensive journey, through one of Italy's greatest engineering achievements, namely the construction of Italy's high-speed rail network, the Alta Velocità in Italian, from the pioneering tunnels beneath Bologna and Firenze, and I think I could recognize some of the data from Bologna that were presented in Roma at TC28 by Rodri Farro, if I'm not mistaken, and also this vision of next 1,000 kilometers towards southern Italy. I'm a southern Italian, so I'm really pleased by this. So through clear data, including financial data at the beginning, which I really appreciated, because these things are always a bit shaky for the public opinion, technical details on geotechnical conditions and excavation procedures, historical perspective. I think that the first tunnel was a Roman tunnel from 76 AD, and then we went to Frejus and Bologna, Firenze, 1934, and so on. And I think that this lecture has shown the transformative power of infrastructure. Very early in the lecture, there was smarter, greener mobility, serving people, so serving people's mobility. One should remember that our engineering job is a job about society, improving society. I think this is super important. And also, I was really pleased by this data-informed design and construction. So we're always talking about data-informed design and construction. And of course, here at Cambridge, I am, old school, so I haven't done a lot of digital twinning and all this, neural networks and stuff, but solid, robust collection of data during design and construction. How confident can you be with your CFD simulations? Well, you do some simulation, you collect some data, you make sure that these two things match, and this giving you confidence for further design, so that I liked very much. Perseverance, I think that this was another thing, it's been going on for a very, very long time. But what I'm saying is that all of this can turn the geographical and geological challenges, of which Italy is very generous. Italy is full of geological and geographical challenges, and maybe that's why the 40 million euros per kilometer, which is something that you right at the beginning. But this can be changed into opportunities for growth and progress. Another figure that was right at the beginning was 20 million tons of CO2 saved. And another figure that I was very impressed with is how the number of journeys by car and plane have really reduced in Italy. I mean, I remember when we used to drive to Milan or take a flight to Milan. Now, nobody would ever dream other than taking a train. You have internet, you work, it's only 2 hours 45, perfect. So this is important. This, again, changing the attitudes, remembering that, you save CO2 not just during construction, you save CO2 by changing people's attitudes. So these are opportunities for growth, progress. And, okay, so I think another point is that your lecture today has reminded us, or definitely me, that often what goes on underground, so in this case in tunneling, but also in the quiet offices of people designing, things that are not so obvious, can really shape the world above. So, we are doing something underground and we're shaping the life above. And so, on behalf of Cambridge, CSIC, and all of those that are gathered here, I wish to thank you for sharing your knowledge, your experience, and your passion with us. Thank you again. Thank you.